Hey, AP Chem. So we're going to continue here with oxidation reduction reactions. This is the last section in chapter 4 that we need to cover. And we're going to start by talking about cell potentials and then go into balancing redox reactions that aren't quite as easy to balance. So stay with me. We'll do this one in class together too. Okay, so this brings us to our next concept within oxidation states, oxidation reactions. If the electrons can be forced to run through a wire, they can be used to produce electricity. And so we need to be able to talk about the amount of electricity they are going to produce, which brings us to E. Now, you won't actually see it written like this. You'll see it written more like that. And this is called the cell potential. It's how much work, basically, the cell could possibly do. It's going to be measured in volts. Okay, before we do practice, let me explain the concept to you. So each reaction has the potential to give off electrons or take in electrons. Now, every time you have someone that loses electrons or is oxidized, you're also going to have someone who gains electrons, which is reduced. These two things can never happen apart from one another. They always have to happen together. If you have oxidation happening, you will have reduction happening. If you have reduction happening, you'll have oxidation happening. If you have someone giving off electrons, you must have a place for those electrons to go. If you don't have anyone who's willing to accept electrons, you can't give away your electrons. They have to happen in tandem. And so what happens, what chemists do is they look at these reactions and they pull out the part that is able to give off electrons, and then they pull out the part that is able to accept electrons, and then they write them as a half reaction. They write them as only the oxidation happening or only the reduction happening, and then they can say, for this half of the reaction, here is the cell potential. For this half of the reaction, here is the cell potential. So when we put them together, what is our total cell potential? So I want to show you one of these charts. It's called a reduction potential chart, something to that effect. Let me show you one of these. All right, for example, let's use the one that we're going to see the most clearly. How about this one? Nope, we don't want Gibbs free energy. Get out of here. How about this one? Here we go. Okay, standard reduction potentials. Is that going to work? That's not going to work. All right, let me see if this works. Copy. All right, here we go. So you can see here that we have half reactions for a lot of these things. So for example, let me pull you out a simple one. Here's iron. Oh, actually, let's do the silver one above. Actually, we'll do both. Okay, so notice that these are listed as standard reduction potential. So they pulled out all of these half reactions. Look, silver, it's going to gain an electron and it's going to turn into solid silver. And it has a reduction potential of 0.8 volts. Now notice, silver is being reduced here. Silver is gaining an electron and it is being reduced. all of the things listed in this chart are being reduced. So if you want them to be oxidized, you have to flip the whole reaction here. So I can flip it. Okay, now I have silver, and that silver is going to split into the silver ion and one electron. And in this case, the cell potential would be flipped also, negative 0.8 volts. Okay, so if the silver ion is reduced, that has the potential to produce 0.8 volts. If solid silver is going to be ionized, is going to be oxidized, we are going to need to input 0.8 volts. And so that positive versus negative tells you what direction the energy is going to need to be coming from. Is it going to be given off? Is it going to be taken in? And we can manipulate these because, like I said, anytime you have something that's being reduced, you must have something that's being oxidized also. And so we can manipulate these to make them oxidation. Now, if you were to combine two things, you can combine them to get a complete reaction, something that's oxidized plus something that's reduced. So I could take silver and I can combine it with iron here. Now notice silver is the ion that goes to something solid. That's not always the case. In iron's case here, we have iron 3+ and it goes to iron 2+. Okay, so we can have something that just changes ionic form here. Now I can't add these the way that they are currently standing there because they're both being reduced. I have to flip one so that I have one being reduced and one being oxidized. Now, as we do this, let's start with silver. Okay, Ag plus E minus goes to Ag. E is 0.8. And then I'm going to flip silver here. So Fe2 plus goes to Fe3 plus E minus. And then I have an E for that also. Since I flipped the reaction, I'm also going to flip the charge. So negative 0.77. Now notice a couple things here. I have an electron that is being taken in by silver. I also have an electron that is being given off by iron. And so I have someone who's giving and someone who's taking. That's really important. You need an electron on both sides. The other thing is you need the same amount of electrons on both sides. If I had paired silver with iodine, for example, right here, notice that iodine takes on or gives off 2 electrons. So in that case, I would have had to double the silver reaction. So I would double silver plus, I would double E minus, I would double Ag, I would not double the cell potential. So that's really, really important. You can double all of the whole reaction, and it does not double the cell potential. If you want to know more about this, you really should take physics. They go into all of these like current, voltage, resistance. They go into all of these concepts that have to do with electricity. And cell potential kind of has to do with, like, if you're talking about water in a river, it would have to do with the height of the waterfall, right? If you have a higher waterfall, you have more potential to do work, right? But there's other factors that are at play here also, like how much water is flowing through your river. Is it a skinny stream? Is it a fat stream? And if you double the cell potential, you are implying certain things about this waterfall that are not necessarily true. So this is just something you're going to have to remember. You can double the reaction, do not double cell potential. Okay, so we've flipped it. We're going to add it. A plus Fe2 plus E goes to Ag plus, I don't know if you can see my blue very well. Let me slightly change that, Fe3 plus E. And now anything that appears just like in a net ionic equation, anything that appears on both sides, you want to reduce out. So I have an E on one side, I have an E on the other side. I'm going to reduce those out. Electrons should always reduce out of your equation if you have balanced it correctly. And I'm going to get Ag plus Fe2 plus goes to Ag plus Fe3 plus. So now I have a complete oxidation reduction reaction. I have something in here that is oxidized. I have something in here that is reduced. Okay, it's a complete equation. And in order to find the cell potential of this equation, I'm just going to add my cell potentials of the two halves. So E equals 0.8 minus 0.77. So I'm going to get a 0.03 volts. Now, if your E comes out as positive, that means the reaction will happen spontaneously. So if you leave it alone, do nothing to it, it'll happen. It also means it has the possibility to generate electricity. Okay, if your E came out as negative, then it would mean that the reaction is not spontaneous. And in order for the reaction to occur the way you have it written, you would need to pump electricity in order to drive it forward. All right, we will practice one of these together also in class when we get back together. Okay, good job today, you guys. Okay, so when we are looking at reactions like this, you see that these reactions have to be balanced not only for the elements themselves, but also for the electrons. So, for example, if I have, let's look at silver again. Silver to silver. And then let's also look at lead 2. Okay, so here are two half reactions. They're both written in terms of reduction. And when we want to combine them, we need to combine them so that one of them is oxidized, one of them is reduced. We need to combine them so that all the elements are balanced, just like a normal reaction. But we also need to look at if the electrons are balanced also. If one of them is going to give up one electron, the other one can't just take on 2 electrons. One electron isn't going to magically appear out of somewhere else. So if one's going to accept 2, we need someone else who's going to give off 2. Okay, so let's kind of break these down bit by bit. So first of all, we need to flip one, and we're going to flip based on the cell potential again. I think silver is somewhere around 0.8. I'm not sure what lead is, so let's just make one up for lead. Let's say lead is 0.55 volts. This is in volts. Okay, so remember, if you want it to be spontaneous, you need the total cell potential to come out positive. So we're going to flip the second one in this case. So let's totally flip it. So lead, instead of being a product, is now a reactant. The lead 2 ion and the 2 electrons are now products, and I'm going to flip the cell potential to be negative. Okay, so now I can add them up, but now we need to look at balancing the electrons. So silver is going to combine with 1 electron, but lead here is giving off 2 electrons. So like I said, if someone's going to give off 2 electrons, someone else needs to accept 2 electrons. So we're going to double this top one. So we're going to have 2 silver ions, 2 electrons, 2 silver elements. And then remember, the cell potential does not get doubled. Okay, so now I have electrons balanced. I can combine and reduce out. So 2 Ag plus, Pb, 2E minus, 2 Ag, Pb2 plus 2E minus. And then if I wanted total cell potential, I could add those as well. All right, so now I'm going to reduce out spectators. So the electrons get transferred from one thing to the other thing, but you don't actually want to include them in your final version. And then the last thing we need to check is, are all my elements balanced? And the answer is yes. I have 2 silver, 2 silver, 1 lead, 1 lead. So now I have a balanced, complete reaction. Now, unfortunately, in redox, not everything is this simple. So when your reactions include oxygen or hydrogen, they're definitely not this simple. If you go back to that chart, you'll find certain things like manganate is a really good example. So we can have manganate on this side, but on the other side of the reaction, manganate actually gets changed into the manganese ion. So where does oxygen go? And you'll notice as you look through that chart, the same thing happens with hydrogen. Oxygen and hydrogen usually just kind of drop out of these half reactions unexpectedly. And so when you are balancing redox reactions, we have to go through a couple additional steps to make sure that not only is our elements balanced like a normal reaction, we also want to balance electrons, and then we also want to double check our oxygens and hydrogens balance. So I'm going to step you through one method of balancing redox reactions to make sure that all of these boxes are checked, all of these things are addressed and balanced correctly. And it's called the half reaction method for balancing redox reactions. It's kind of complicated. It's kind of long. Stay with me on one, and I'm going to explain. I really want you to listen for the reason that we're doing things, because if you understand the reason, then it's not just a whole bunch of steps to memorize. You'll understand kind of the why we're doing things, and you can reason your way through these. Okay. So we're going to balance this one. Hey, look at that. Manganate is in our example. We're so good at life. All right, so here's our reaction, and you can see I do have something being oxidized. I have something being reduced, but not everything is balanced. I'm certainly missing electrons in here. I don't know if my electrons are balanced. My elements aren't even balanced at this point in time, and then certainly not my oxygen. So in order to make sure all of these things end up being balanced, we're going to go through the half reaction method. So the first step in the half reaction method is to separate your half reactions. So you're going to take everything that's manganate related and separate it onto one side, everything that's carbon related and separate it into another side. So MnO4 minus, Mn2 plus is going to be on this side. And then on the other side, I'm going to have C2O4 minus and CO2. Okay, now step 2, I want to balance every element that's not oxygen or hydrogen. So manganates are balanced, oxygen's not, but I'm ignoring oxygens and hydrogens for now. Carbon is not balanced. Okay, so in step 2, let's make step 2 this color. I'm going to go ahead and balance my carbon, 2 and 2. Again, oxygens and hydrogens may not be balanced, and that's okay. All right, step 3. We're going to balance. Here, let me make some notes. Step 2 is every element except oxygen and hydrogen. Okay, step 3 is going to be oxygen using H2O. Okay, so we're going to balance oxygen now, and we're going to use water in order to balance oxygen. Now, remember, these reactions are happening in solution. That's why we're dealing with them in chapter 4, right? Our chapter 4 is all about chemistry and solutions. And so these reactions are happening in solution. So it really doesn't matter if we add water into these balanced equations because there is an abundance of water. This whole equation, this whole reaction is happening in a bucket full of water. So we can add in as much water as we want. It's there. It's just not always listed because it's not always changed. But if we want it to be changed, it can definitely be changed. So we're going to balance oxygen using water. The second reason we're going to balance oxygen first is notice water involves hydrogen. So we don't want to go through and balance hydrogen and then add water and screw up our hydrogen again. So we're going to do oxygen first, so that we can go through and then correct hydrogen after that. So I have 4 oxygens on this first side. I need 4 on the other side. So I'm going to add H2O, and I need 2 of it, so I get 4, not 2. I'm going to add 4 of them, so I have 4 oxygens on one side, 4 oxygens on the other side. Okay, now in my other half of the reaction, I have 4 oxygens on one side and 4 oxygens on the other, so I actually don't need to add water to that one. All right, now I'm going to go step 4. Now I'm going to balance my hydrogens using H+. Now, the only thing you need to do in lab to make sure you have H+ available is acidify your solutions. You just add a little bit of acid and then you have hydrogens floating around that can be used in the equation, but don't necessarily have to be used. So again, it's kind of like the water. It's there floating in the background, and if we need it, it's there for our convenience. Okay, so on the manganese side, I have 8 hydrogens on one side, so I need 8 H+ on the other side. And then in my carbon side of the equation, I actually don't need either. All right, we are rolling. All right, here is step number 5. Step number 5, we're going to balance electrons. Now, we balance electrons just by adding electrons where they're needed, but figuring out where the electrons are needed is the tricky part. Okay, so let me show you how this works. We have to add up all the charges on both sides of the equation. So MnO4 is a -1. Here, H's are a +1, but I have 8 of them, so 8 pluses. So these two things are going to add up to a 7+ on one half of the equation. On the other half of the equation, I have a 2+, and then I have 4 waters, but waters are neutral, so that doesn't add anything to me. Okay, so on one side of the equation, I have a 7+. On the other side, I have a 2+. I need that to be balanced. So I'm going to add electrons until it is. So this side of the equation needs 5 electrons. And then I'll have a 2+ and a 2+. Now let's do the same thing with the carbons. This side is a -1. This side is a 0. So I'm going to need 1 electron on this side so that I have a -1 and a -1. All right, moving right along. Step number 6, we need to balance electrons again, but this time looking at the 2 halves of our reaction. So if I have 5 on the manganese side and 1 on the carbon side, I'm going to just multiply this entire side by 5. So that gives me 5 C2O4 minuses, 10 CO2s, and 5 electrons. Now I have 5 electrons on the manganese side, 5 electrons on the carbon side. All my elements are balanced, my oxygen is balanced, my hydrogen is balanced, my electrons are balanced. Woo! Now we can put it together. All right, so I have 5 electrons plus MnO4 minus plus 8 H pluses plus 5 C2O4 minuses. That is my reactants. And on the product side, I have Mn2 plus 4H2O plus 10 CO2 plus 5 E minus. Now I need to go through and eliminate things that appear on both sides, like 5 electrons, and nothing else. Everything else is unique. Now, if, for example, I had like 6 waters on this side and 4 waters on this side, what I would do with this is I would take out all of the waters and I would end up just with 2 waters on the left side and 4 on the other. So that's if water appeared on both sides of the equation and I needed to reduce them out. Or same thing might happen with your hydrogens. Sometimes you have hydrogens appear on both sides of the equation, but in this case, I don't. And so this actually is my balanced equation. Now, again, if you're dealing with a free response problem, you don't just want to cross things out and then box the stuff that's not crossed out. You do want to rewrite it and box it. It's going to take you literally less than 5 seconds. It's a good dedication of your 5 seconds. Now I want to show you one more thing on this. So this is going to be my equation as it happens in acidic solution. If it happened in basic solution, I would need one more step. My 7th step would be to switch it from acidic to basic. And the way you do that is you add hydroxides. So I want to get rid of my H pluses because H pluses indicate an acidic solution. So I would add 8 hydroxides to both sides. If I add it to both sides, I'm not really changing anything, right? So now I don't have 8 H pluses and 8 OH minuses. I have 8 waters. And now I do have waters on both sides. I have 8 on one side and 4 on the other. So that I can also reduce down. So minus 4 on this side would give me 4. Minus 4 on this side would give me 0. And so if I was going to balance it in basic solution, I would get this. And you'll see that instead of being left with H pluses in my balanced reaction, now I'm left with hydroxides in my balanced reaction, which indicates a basic solution. Okay, so if you're balancing it for acidic solution, there's 6 steps. If you're balancing it for basic solution, there's 7. So again, those steps are going to be split them into half reactions, balance everything, every element except for oxygen and hydrogen, balance oxygen using water, balance hydrogen using H+, balance your electrons within each half, balance your reactions between the two halves, and then eliminate any spectators. And you're done unless you have basic solution, and then you have to go through the hydroxide section. Okay, again, I know it's a lot of steps. It's a lot of steps. Go through a couple of these, try a couple of these in your book, and then come back together and we'll do one together also. I swear, like this is, it is not a tough concept to get. It is just tough to get all the steps in the right order, and it's really easy to miscount. It's so easy to miscount. So we'll just step through a couple together, and once you get the rhythm, you're like, oh yeah, this isn't so bad. It's just remembering all the steps. Now, fun fact, they've never asked this on a free response question, which is good, but they have asked this on a multiple choice question. So the question becomes, is this worth your time and effort to memorize it? And I say, yes, it's worth your time and effort because it's such a fundamental concept for electrochemistry. So if you go into like chemical engineering or electrochemistry or something in that direction, you're going to want to know how to do this. And it's nice to like see it and walk through it a couple times and really try to learn this. And then when you have to come back to it, you'll be like, oh yeah, I remember that. I can handle that. So that's why we go through it. Is it worth missing one point in the multiple choice? Maybe it's worth missing that one point, but I do want us to walk through it a couple times and see if you can find that rhythm. Okay, this is the one we're going to try together in class. So we'll do that next time we get some practice time together. Okay, so a couple special types of oxidation reduction reactions I just want to point out to you. So when you're dealing with redox reactions, like I said, it always usually fits into those 5 big types of reactions, especially combustion and displacement reactions. So single displacement, especially, sometimes double replacement also. If you ever have a metal and a salt or a metal and an acid, a light bulb should go off, a red light should go off in your head, and you should think corrosion. Like if you put a metal into acid, it's going to corrode, right? That's going to be redox. If you put a metal in salt, if you rub salt on your metal, you're going to corrode it, right? That's redox. So these things should just trigger a red light to you, like, hey, I'm dealing with a redox reaction here. So here's a couple examples. Here's our basic single replacement structure, right? The metal replaces another metal. And then you basically get a new salt out of it. So zinc in hydrobromic acid, you're going to get out zinc bromide and hydrogen gas. And then manganese and lead nitrate. So again, a metal and a salt. In this example, you're going to get out manganese nitrate and then lead. So whenever you have something like lead, like in this case, you have lead 2 nitrate. Sometimes you start with, if lead is the metal that you're flipping in to the salt and you don't know if it's going to end as lead 2 or lead 4, usually you can guess because both of them are probably going to form to some extent. One of them is going to be favored over the other one. But usually if you have to guess as to which ion it's going to form, same thing with like iron. Will it form iron 2 or iron 3? Same thing with copper. Will it form copper 1 or copper 2? Just guess. If you're familiar with it, if we've dealt with it in lab, guess the one we did in lab. But if you're not familiar with it, just put one of them down and they're probably going to give you either one. Okay, so again, this is a good practice one. We can go through and do it together. And then we can also practice identifying. Can you identify which one is oxidized, which one is reduced, which one is the spectator ion? Since we have 2 of these, let me go through and do the first one for you. So we'll end up with manganese chloride plus hydrogen gas. And we'll have to balance this. Okay, so those are the products. Now, what's oxidized, what's reduced, and what's a spectator ion? This would be a really good time to pause the video and see if you can come up with this first. All right, so in order to figure out what is oxidized and what is reduced, we have to assign oxidation numbers. So 0 plus 1 plus, not plus 1, minus 1, 2 plus, each one of the chlorines is a minus 1. So I'll say times 2. And then hydrogen is going to be a 0. Okay, so let's look at the changes. Manganese goes from a 0 to a 2 plus. So it's going to lose electrons because it's becoming more positive, which means manganese is oxidized. And then chlorine doesn't change, -1, -1. hydrogen goes from a +1 to a 0, which means it's going to gain electrons. It's becoming less positive. So hydrogen is the thing reduced. There we go. So I would say manganese is oxidized. You can say either, actually, I would say HCl is reduced. You could specify the H plus in HCl if you want to get really specific. And then chlorine, or the chloride ion, is going to be our spectator. Okay, so we can practice one of those together in class next time. We'll do the metal salt example. And then same here, we can practice this one together. Okay, so this leads us into the activity series. If you are looking at metals replacing other metals, so for example, let's say I have like silver and copper to chloride, and it goes to copper plus silver chloride. Okay, so the question would be something like that. Actually, your question would probably be something like that. Okay, silver is going to be mixed into copper chloride. Will this reaction happen? And so this was an activity we dealt with in chemistry also, where we dropped metals into solutions. So we dropped a bunch of different metals actually into copper to chloride solution. And then we kind of watched to see which one of them reacted faster. We didn't use any quantitative data to figure out which one reacted faster. We used all qualitative data, like what does it look like? Do I see the color change? Is there something disappearing? Is there something appearing? How quickly is it happening? So our data was more of a ballpark than anything else. But what we were trying to establish in asking ourselves which metal reacted faster was an activity series, because some metals will replace other metals in these compounds, and some metals will not replace other metals in these compounds. And that has to do with how active the metal is. And we can actually rank metals based on their activity. And I believe we told this like quirky little story about Mr. Iron maybe going to the dance with Miss Chloride. And he's kind of slumming it a little bit and not really treating her like a lady. And when they get to the dance, she sees her good friend, Mr. Copper, and he always shows respect to her and is always very kind. And so she ditches Mr. Iron and joins with Mr. Copper. Oh, no, it must have been the other way around. Mr. Copper must have been the one who was slumming it. And she ditches him and goes for Iron. And the whole crazy story is supposed to like lead you into this idea that there's some metals that are very happy by themselves. There's some metals that don't need a partner at the dance, like Mr. Copper. Mr. Iron really wants a partner at the dance. Mr. Copper doesn't need one. And so there's all these metals that are very happy and very stable all by themselves. And if you think through like jewelry and coins, you can probably identify these metals like platinum, gold, silver, copper. These are coin metals. And the reason they use them as coin metals is because they're so stable by themselves. If you leave them in your pocket or in your car or anywhere, mostly except a puddle on the side of the road, in your pocket, they're going to be very stable and they're not going to corrode. Whereas if you had a coin made out of lithium, for example, the minute lithium gets uncapped and comes in contact with the water in the air even, it's going to turn into this fireball and settle itself into being an ionic compound as a salt. It's much more stable in a compound as a salt than it is by itself. And so those coin metals are lower on the activity series because they are not as reactive as the active metals like lithium and magnesium and sodium. So the activity series can help you figure out, will a reaction happen or not? So if we look at the activity series, here we go. If we look at the activity series, things on the top, they want to be in compounds. They are more stable in compounds. Things on the bottom are very stable by themselves. So if we look at our two examples, we have copper and we have silver. Well, silver is below copper on the activity series. Silver does not want to be in a compound. And so this is a no reaction situation. Silver is much happier being alone than copper is. And so no reaction will happen here. Silver will just continue to sit on the bottom. Copper chloride ions will float around, mingling with each other, and no reaction will actually happen. Whereas if this was switched, if we had copper and silver chloride, then copper will actually replace silver. So you'll get copper chloride here and silver by itself. And this reaction will happen. And so you should generally know, like, coin and jewelry metals are less active. Some of the alkali metals, especially the high alkali metals, those are going to be super active. You should generally know some of these, but the specific ranking of them, you should basically be able to use the activity series. And all of these reactions that we're talking about like this, they're oxidation reactions. Metals being oxidized by acids, metals being oxidized by salts. Okay. So this is a good practice one we can run through together. More practice ones we can run through together. Okay, and that's it. That is chapter 4 for us. So now we want to run through this practice together. We want to try the problems in the book and ask questions off of that, and then we will be ready to take this quiz. Good job, you guys. Let me know if you have questions.